So if we want to know the tension in the rope and the pin reactions at A, if we take the steel plate as our object of interest here, we're going to have the pin reactions at A. We'll have the tension in the rope at B. So what other forces are going to act on our object in the free body diagram? Right, in this case, we're not ignoring the weight, so we have to account for gravity somewhere, and this is where the problem arises. We can't just put it in the middle because it's not just a rectangular shape. So it's going to have some weight. Also, we don't know what the weight is, acting at some point that we don't know exactly where that is at the very moment. So we have to, the way we can solve this is if we know where its centroid is, that's the place where we can put the weight, and externally we'll get our answer. And also to find the weight itself, we're going to need to find the area of the shape because they tell us for this shape what its thickness is. It's a uniform thickness, and we're told its density. So with all of that information, we'll be able to find the actual weight of the steel plate. So if we look, we have AX, AY, and T we don't know. We also don't know at the very moment W or where W should be placed that's going to externally be equivalent. So we won't be able to find some of the aspects with equilibrium equations. We'll find them with calculus.
Would you want us to label, like, that, as a free body diagram, would you want us to label that as X, the X and the Y?
Right, yeah, so I can call this X bar and Y bar because I don't know what they are yet, but I'm going to be able to find them in a couple minutes.
When we set up our free body diagrams, that's essentially...
Right, so this is, and this tells us we don't know enough. The three equilibrium equations aren't sufficient to solve for everything we need.
So for the free body diagram, do you want like the y cubed equals 2x in the free body diagram?
For that, no, it's not important here. It'll be important once we get to the math step of this. Yeah, because really, it doesn't matter what the shape is. It could be a rectangle or any other shape. If the center of mass was at that location, the rest doesn't matter. All right, so that's our free body diagram. We're going to come back to it because we see there's too many unknowns. There's 6 unknowns. 3 of them we're going to solve through use of centroid. So now I can take that, and now it's important what that function is. Y cubed equals 2x. And we know this is 4 meters. We know this is 2 meters. So we want to find the centroid of this so that we know where to put the weight. So we have to decide, are we going to would we prefer to use a vertically oriented rectangle or a horizontally oriented rectangle? So again, kind of the clue of which might be easier comes from what functions are involved. So here we just have a vertical line and a horizontal line, so those don't really influence our decision. But we want to look at when we isolate x or isolate y, which is going to be a nicer function to use. So if we isolate x, we can get that x equals 1/2 y cubed. Or we could isolate y, and y is going to be the cube root of 2x. Looking at the top one, the right-hand side here is going to be easier to integrate by hand than trying to integrate the cube root. So I'm going to say I want everything in terms of y, which means I have to use dy, which means I would prefer to use a horizontally oriented rectangle. Again, if everything's in terms of y, this is the type of function I'm going to be integrating as the y cubed, rather than the alternative, which I just erased, which would be the cube root of x. Both will get me my answer. This will do it a little bit easier, though. All right, questions on my choice of a horizontal rectangle for this problem? All right, so same steps as before. I want to find the area of each triangle. So now the height of each one I know is always going to be dy. So what I want to find is what is this length going to be? So it's going to start here and end here. So the right-hand side of every rectangle I draw is going to be at 4. but the left-hand side is going to switch. So how do I define the length of every rectangle then? Everything will, in this case, be in terms of y. So the left side is defined by x equals 1/2 y cubed. And the right-hand side, I'll call it x sub r, is always at 4. So the length is going to be the right side minus the left side. So that's true for every rectangle here. So the smaller my value of x is, then the smaller, my left-hand side then is closer to y. So the smaller this value is, so the larger this value is. All right, so that's the length of every rectangle, is the right-hand side minus the left-hand side, all in terms of y. And again, every rectangle has a height of dy. The y tilde this time is easy, is just y. But now the x tilde is going to be a little bit, not much tougher to find, but just a little bit tougher to find. So this is, again, where you have to be careful when you're thinking about this. X tilde is the distance from the y-axis to the centroid of any one of our rectangles. So in the last case, it was a little bit easier because the bottom of the rectangle was on the the x-axis. Here, that's not the case. The left-hand side is not always touching the y-axis. Yeah. So generically, we could write it like that. So this XL distance plus half of the length, which we decided was XR minus XL over 2. That's how we got this length here. More simply, we can write this as XL plus XR over 2. So it's just going to be the average of the left-hand side and the right-hand side of the rectangle. And then this will always be the case. So our left-hand side, again, was defined by 1/2 y cubed. Our right-hand side was x equals 4. We can divide that by 2. So this will simplify 2. I wrote it as 1/4 8 plus y cubed. So x tilde, XL, the average of XL and XR, dA is going to be XR minus XL in the most kind of general sense. Yeah.
Could you go over what like y tilde and x tilde is again?
So the tildes are it's the location of the centroid of every differential rectangle. So it's this as measured from the x-axis for y tilde and the y-axis for x tilde. The x bar, y bar is the centroid of the entire shape, also as measured from the origin. All right, questions on dA, y tilde, x tilde? All right, so now we just go into the calculus. So the area of the shape is going to be the integral of dA. So 4 minus 1/2 y cubed dy. We're integrating with respect to y, so our bounds are also with respect to y. So we're, in this case, stacking the rectangles up. So our first rectangle is at y equals 0, and then the topmost rectangle is at y equals 2. So see how this is different? If we had used a vertical rectangle, we would start them at x equals 0, but we wouldn't stop until x equals 4. So the bounds of integration are going to be dependent on the orientation of the rectangles that we use. Again, everything is in terms of y here. We can take the antiderivative of this, so we get 4y minus 1/8 y to the 4th. Evaluated between y equals 0, y equals 2. So the total area of the steel plate is 6 square meters. just like in the last problem, we can find now, I'll go y bar next since it's going to be easier than finding x bar. So integral y tilde dA. So same bounds of integration. Y tilde is just y. So we're going to get 4y minus 1/2 y to the fourth. Yes, right. Forgot about that part, which we already know is 6. Finding the antiderivative, we get 2y squared minus 1/10 y to the fifth, evaluated from 0 to 2. This will be 4.8 over 6, which is going to be 0.8 meters. And then finally, x bar will be x tilde dA over A. X tilde is a little bit more complicated here. I can take that 1/4 out. So 8 plus y cubed times dA, 4 minus 1/2 y cubed dy. I'll skip a little bit of the math. You can FOIL this out. It's still a polynomial, but it's going to work that the antiderivative is 8y minus y to the 7th over 56. Evaluating it at y equals 2 and at y equals 0, we get 13.7 for the numerator over 6. So 2.29 meters is the x bar location. So again, this is just calculus. This is removed from the problem at this point, but we're going to now use this back in our free body diagram. Questions on these three values here? So because this is a homogeneous structure, we can now put in the information that we just learned. So we now know where the centroid is located. So it's going to be x bar from the left-hand side, since that's where our origin was in this picture. So x bar is 2.29 meters. So we now know this is a number. And we now know the value of y bar is 0.8. And the area we can use now, we want to find the weight of the object. So the weight is going to be the density times the volume times gravity. We were told the density of the object. The volume we can now compute because we know it's a uniform thickness and we know its area. And then gravity is just a constant. So this is going to be 7850 kilograms per meter cubed times volume is just the area times the thickness. So the area was 6 meters squared times the thickness, which they tell us is 10 millimeters or 0.01 meters. Times gravity, which is 9.81 meters per second squared. We have meters cubed, meters squared, and meters up here. So what we're left with here, when we go through all the multiplication, is that the weight is 4,620 kilogram meters per second squared, which is a Newton. So the weight of the entire plate is 4620 newtons. So that, again, the purpose of the centroid is externally we can put that entire weight at the centroid and figure out externally what these reactions are going to be. So now it looks just like a chapter 5 problem. We're left with these three supports that we don't know. So if we take the sum of moments around A, is going to be equal to 0 is going to be negative 2.29 times 4620 plus 4 times t. So the tension in the rope for this to be in equilibrium is going to be 2,650 newtons. Forces in the y is 0 is AY plus T minus 4620. So AY is going to be 1,980 newtons. And the x direction, we only have AX in this problem, so AX has to be 0.